Okay, this is exam 2 review 2020 fall. Okay, number 1. Which of the following is aromatic? Now, for a compound to be aromatic, you should remember that it should have conjugation throughout. It must be conjugated. Of course, it must be cyclic, and it has to be flat. And when you solve for n in 4n plus 2 equals number of pi electrons, n must never be a fraction. It could be 0 or any whole number. So if the molecule passes all these 4 cyclic, conjugated, planar, and passes 4n plus 2, it's gonna be aromatic. So the first one, we have a nitrogen. Now you notice that these nitrogens have lone pairs, but because you already have a pi bond to the nitrogens, the lone pairs will not take part in resonance. So those lone pairs are not part of the pi electrons. So the only pi electrons we have are the ones in the double bonds. So there's 3 pi bonds, so there's 6 pi electrons. Okay, so I like getting that out of the way, okay, to take care of rule 4, which to me is really supposed to be rule number 1. So if this is the number of pi electrons, if you solve for n, okay, n is gonna be equal to 1. So it passes that rule. Conjugation, yeah, it's conjugated. You have a pattern of pi bond, single bond, pi bond, single bond. These double bonds can go all throughout the ring by resonance. Whenever you're thinking conjugation, think resonance. Of course, it's a ring, so it passes. Is it planar? We need these elements to be either sp2 or sp for the molecule to be planar, because sp2 hybridized elements or element centers, atom centers, are usually trigonal. Planar in molecular geometry, they're flat. So like here, there's a hydrogen, there's 3 electron domains, 2 single bonds and a double bond. So this is sp2. So you will expect all these carbons to be sp2s. What of the nitrogen? The nitrogen 2 has 3 electron domains, lone pair, double bond, single bond. So it's also sp2. Everything is sp2. So the molecule of aroma must be planar. So this molecule is actually aromatic. It's aromatic because it checks for all these rules. Okay, so A passes. What of B? Is B aromatic? So we do the same test. And I already see that B is not aromatic because this carbon right here is tetrahedral. That center is tetrahedral. This molecule, the carbon is sp3. I told you, you really want either sp2 or sp. So this guy is gonna be tetrahedral. That center is gonna be tetrahedral. So which means it's not flat, it's not planar. The other reason why this molecule is not aromatic is because you cannot push this double bond here. There's no plus sign on this carbon to do resonance. So again, it's not conjugated. So it fails those two. So this guy is not aromatic. It fails at least one of the rules. In this case, it's failing 2 of those. And then let's try C. For molecule C, it's drawn like this. It's a cyclopentadiene carbanion. So there's a hydrogen here, it's implied. You see, I can push this to make a double bond there. This will move over, right? And this opens up to come here. So all the pi bonds are affected. So This guy is conjugated because we can do resonances. There's resonances. It's conjugated. Check. Of course, it's a ring. Is it planar? It has to be planar. The reason being, on this carbon right here, let's check, do the hybridization test. This carbon right there, that carbon is having 3 electron domains. I'm not counting the lone pair because this lone pair is taking part in resonance. It's not available to be counted. So I only have the 3 single bonds. So the carbon right there is sp2. Okay, that would have been the catch for hybridization. You would think it's not sp2. This one is sp2. This one is sp2 carbon. This one also is sp2. And also this guy was sp2 before resonance and even after resonance. Okay, so the molecule is planar because sp2 molecular geometry is trigonal planar. You know that as trigonal planar for sp2 hybridization. Next, we have to check for the value of n. If it will solve for 0 or a whole number, 4n plus 2 equals to number of pi electrons. So how many pi electrons do we have here? Those are the electrons that are taking part in resonance. It's going to include this lone pair because we even did not count it as a domain. So that's how we were left with 3 bonds that gave us 3 electron domain that gave us sp2 hybridization. But this time we're going to count it as pi electrons because they are taking part in resonance. They are affecting the other pi bonds as you push them around. So you have those 2 and you have the 4 in the 2 pi bonds. So you have 6 pi electrons. So we'll put the 6 pi electrons here. So 4n plus 2 equals to 6 pi. You'll see that n will solve for 1. So it passes everything. So C is aromatic. So far we've found that A is aromatic and C is aromatic, B was not. So now we test for D. Is D aromatic? You can see I can push this one here and it's gonna give me a resonance structure that looks like this. Where the double bond left, there's gonna be 1 bond less, put a plus sign. And again, this can be dropped here. Gonna get a new resonance structure. Where the pi bond left, we're gonna get a plus sign. So this molecule is conjugated because we can do resonances. Okay, it's a ring, no doubt about it. You see it's a ring, it's cyclic. Is it planar? The answer is yes. How do I know that? Because I see all these carbons are sp2 hybridized. That's sp2. Here you have a hydrogen, 3 bonds, 3 electron domains. That's sp2 trigonal planar. The same case with this. There's a hydrogen. You have a double bond, a single bond, a single bond. It has to be 3 electron domains, sp2. So yes, it's planar. All those carbon centers are sp2 hybridized trigonal planar molecular geometry. And now we test for the main test for n plus 2 pi electrons equals to how many pi electrons do we have? We only have 2 pi electrons, which are in the pi bond, 2. So in this case, for n equals to 0 and n will be equal to 0. So that passes because we said that whenever you're using this law, this rule, n should be 0 or a whole number. You just don't want it to be a fraction. So 0 is part of our positive test. All right, so far A, C, and D are aromatic. That answers question 1. Okay, moving on. Moving on. Question 2. Which of the following pairs are not the same? 3-chlorophenol. So let's look at A. 3-chlorophenol. Remember, it's a phenol. It's just has an OH on the 3rd position. That's the 3. You have a chlorine. That versus 5-chlorophenol. 5-chlorophenol. So I assume this is position 1, 2, 3, 4, 5. These two guys are the same. They're just flipped over. So this that's correct. Those two are the same. We are looking for the ones that are not the same. B, 3-chlorophenol. 3-chlorophenol is exactly as what I drew before. We are comparing that with metachlorophenol. It's the same thing. Remember, next door to OH is supposed to be ortho. Okay, so this position is ortho. The next position is meta, which is here. We still have our double bonds. So these guys are the same. These guys are the same. Same name. Okay, same. And then 2-chlorophenol. So you have a chlorine on the second position from the OH versus 6-chlorophenol. So let's assume you're counting clockwise from the OH. You'll find that this position right here is 6th position right here is the same as the second position. You just flip the molecule. These two guys are the same. D, 2-chlorophenol and 5-chlorophenol, those are not the same. Compare this is 2-chlorophenol compared to the 5th, where the chlorine will be here. These two are not the same. So the answer is D. 2-chlorophenol is not the same as 5-chlorophenol. We are looking for which of the following pairs are not the same. These two are not the same. The answer is D according to my alphabet here. Your alphabet might be different, but the answer is the same. 2-chlorophenol is not the same as 5-chlorophenol. So this is the answer. So let's look at question 3. Question 3. Which of the following structures is chiral? For chirality, you're looking for the one that has 4 different groups on at least one carbon. So I'm just gonna leave it like that. Let's say this is the first structure A. Okay. So you can see we have a hydrogen here. So I at least have 4 different groups around at least one carbon, because this is a CH3. That's different from the CH2, and it's different from the hydrogen. And this CH2 is different from this CH2. Why? Because obviously this CH2 is bound to the oxygen. There is no oxygen here. So all these guys are different. That carbon right there is called the chiral. That's a chiral center or chiral carbon. So A is one of our answers because it's gonna be chiral. We are looking for chiral structures. Let's look at the next one. Structure B, I do have a fluorine, I have a metal, I have an OH, and I obviously have ethyl. So you can see this molecule is chiral because the CH3 is different from the CH2CH3, which is different from OH, is different from F, and that's what we are looking for. We are looking for at least a carbon that has 4 different groups, and the molecule must not have internal plane of symmetry. That's what defines chiral molecules. You don't want internal plane of symmetry. You don't want center of inversion. You don't want a carbon with internal plane of symmetry with the mirror that casts it into equal half. But you do want carbons with, you must have a carbon with at least 4 different, with 4 different groups somewhere. So the last one, this one, I don't think, oh, I think we have one more. This one cannot be chiral because I can carry it into equal half. You see, this part is gonna be exactly the same as that part. So which means these 2 carbons don't have 4 different groups. These 2 carbons do not have 4 different groups. That carbon and this carbon don't have 4 different groups. So this is achiral. That is the opposite of chiral. There's no carbon with 4 different groups. The molecule is symmetrical. You have internal plane of symmetry. That is not our answer. Okay. So next we look at option D, which is this molecule. That's our D. You know there's a hydrogen here, and that already tells me that I have 4 different groups. The ethyl is different from the hydrogen, which is different from the methyl group, which is different from the propyl. You have 3 carbons. So this carbon right here has 4 different groups. There's no internal plane of symmetry. This molecule here is chiral. So we ended up with 3 chiral structures out of the choices. So we've identified the structures that are chiral for question 3. Let's move on. Question 4. What is the main product of the reaction below? Okay, so the first thing you want to understand is OH is an electron donating group. And the way I know that is because the oxygen has a lone pair that can be donated into the ring, making the ring very electron rich and reactive. The next thing I look at is the reagent. Each time you see AlCl3, know that that's Friedel-Crafts reaction. Okay. The question is it Friedel-Crafts alkylation or acylation? I see an alkyl group here, so it's alkylation. Now, I've identified the 2 important information I need, so I come back to the original molecule. So if this OH is an electron donating group, and you do have a table in your book that shows you which groups are electron donating, which are electron withdrawing. Electron donating groups direct incoming electrophiles to ortho and para position. Our electrophile will simply be the carbocation that falls off after the Cl falls off. You have the mechanism in your book. So I would expect from this reaction, I would expect 2 products. This carbocation will go to the ortho position to the OH, which is next door, or directly opposite, which is para. So we have 2 possible products. And so one of the products will have the carbocation right there. That's the ortho product. The other product will have the carbocation directly opposite to the will have the alkyl group directly opposite to the OH, and that will be the para product. Okay, so looking at the choices, the only choice that looks like one of these is gonna be choice A, which is the para product. The answer is A, structure A, structure H, or choice A of the structures. Okay, moving on. I think it's question 4. Question 5. Again, I see a reaction which is electrophilic aromatic substitution. I first of all again see that this oxygen has lone pairs, so it can donate the lone pairs into the ring. So this whole substituent, carrying from there, this whole substituent is an electron donating group. I told you it's gonna direct your electrophile orthopara. On the reaction, I see SO3, H2, SO4. The electrophile that comes from this cocktail is this SO3H plus. That's gonna be what's gonna be added onto the ring. So there are two products, obviously. There's gonna be a product that will have the electrophile attached onto the ortho position. So the ortho position is gonna take the electrophile. Our electron donating group is still there. Alternatively, you're gonna have it on para position because we have an electron donating group. Electron donating groups place incoming electrophile ortho or para. So you can see that the para position here will be occupied by the sulfonic acid. So these are the two options. That will be the ortho substituted product. This will be the para substituted product. Both of them are possible from this reaction. The major one I would have expected to be the para because the SO3H is further away from the inverted ester group, which, like here, you see there's crowding. I keep telling you molecules don't like crowding, but anyway, the two of them are possible. I was not asking for the major in this question. So you can see that you should have given both structure, this structure, which is the ortho, which is structure A, and structure C, which is the para product. Those two are the answers. So let's do question 6. What is the product of the following reaction? This is a nitration reaction. And I again see that I have OH. We by now know that OH is an EDG and it's a strong one because it's donating by resonance. And I am adding nitric acid in presence of sulfuric acid catalyst. So you have NO3 in presence of H2SO4. So again, the second question I'll ask myself, what is the electrophile that's going to end up on the ring? In this case, it's NO2 plus. Now remember, EDG is direct orthopara. So we would draw the two possible products again. So I would draw the ortho product, and I'm gonna put the NO2 after I draw this other ring in white so I don't keep on selecting the colors. So it's either NO2 goes para position or NO2 go ortho position. How did I know that? The reason is because I have an electron donating group. So on here, none of the choices B, C, and D are correct. So the answer is A. At least that's a para. The choices don't have the ortho shown. So we know that the product possible out of the choices given is going to be structure A. Or rather, we call it choice A. This one. Okay. So away from electrophilic aromatic substitution, let us look at question 7. What's the relationship between the following structures? Now, I'm going to remind you something. Enantiomers will have opposite stereochemistry. Regardless of the number of chiral centers, if you have an R center, it's going to be changed to an S, and the two should have no internal plane of symmetry. At the same time, the two of them should be mirror images, non-superposable mirror images. That's why they should not have internal plane of symmetry. non-super possible mirror image. And I explained by telling you to open wide your hands and then cross your left hand over the right hand. You'll see the thumbs are not overlapping. But if you rotate your left hand and match it like you're clapping your hands, your thumbs of your palms will overlap. So your pair of hands are enantiomers. The palms of your hands are enantiomers. For the stereomers, you should have at least 2 stereocenters. For the stereomers, you should have at least 2 stereocenters. One is retained, the other one, at least one is changed. Now, even without assigning R and S on these Fisher projections, let's come from down. You see you have OH to your right, OH to your right, right? In fact, everything down here is the same, the first 3 carbons. Now, when you come up here, you see that this OH is on the left, that's on the left. This is on the right, this is on the left. So you have, okay, the first 3, reading from down, the first 3 pink carbons have the same, have the OHs on the similar sides. Okay, but the last one next to the aldehyde, they are opposite. So you see some of the stereocenters are kept, one is switched, so this has to be diastereomers. All right. Meso compounds is where you would have it should have been like enantiomers, but you have internal plane of symmetry. You can review those in our lecture that concerns enantiomers, meso, and diastereomers and enantiomers. Which of the following is the same or identical? So in this case, what you really needed to do is to assign chirality R and S, and then see which of the choices have the same chirality. So we start with the parent molecule in question. So assign priorities based on Kern-Ingold rules. So oxygen will win. You do have a hydrogen away because the OH is towards, that will be priority 4. Now you can see that this carbon is more substituted than that carbon. So this will be priority 2. And this will be priority 3. Focus on 1, 2, and 3. You can see we are going clockwise. So this one is an R. So we are looking for, out of the choices, we are looking for the one that has an R, but again, the OH must be exactly where it is. We are just, so like, what I mean is, options C and D are wrong because there's nowhere, if you are not to show the wedges, they are not the same, they're not similar to what is boxed. So our answer is either A and B. So looking at A, let's look at choice A and assign chirality, because at least it has the methyl groups and OHs at the right position. So again, that's 1. We said methyl is at 3, we say this is 2, and your hydrogen is at the back is 4. So here we are going 1, 2, 3, and that is an S. We keep the S because the smallest group is away from us. So this is an S. We are looking for one that is same as what's boxed. So comparing A and the original molecule, those two guys are not the same. What are they? They are enantiomers. Okay, remember what I said? Enantiomers, the R will be switched to an S, or the S will be switched to an R. There's no internal plane of symmetry. They are mirror images. Okay, so A is not the answer because they are not the same. Let's look at B. Structure B has the OH away from us, which means the hydrogen is towards us, and we can go ahead and assign priorities. O is 1, hydrogen is 4. This was 2, methyl was 3. Focus on 1, 2, and 3. Okay, we're going counterclockwise. That's an S, but the smallest group, 4, the hydrogen is towards us, so the true assignment is an R. So that's why B structure B is the answer because it has the same chirality as the one that's boxed, and the elements are in the exact positions. So structure B is identical, the same as the one that's boxed, just based off chirality. Which of the following pairs are meso? Remember what we said meso are. You're looking for something that seems to be enantiomer, pairs that seems to be enantiomers, but they have internal plane of symmetry. So the first one, let me just focus here. There's no way you can have internal plane of symmetry in pair 1. Actually, pair 1, these guys are enantiomers because if I put a mirror here, it reflects them, and there's not gonna be any way we can cut the two molecules into equal half. But pair 2 can be cut into equal half. And you're wondering how. You think that if you cut this way, the top half and the bottom half are not reflective. They really are, because you have a center of rotation. This is what I mean. Here is an internal plane of symmetry, and if you can't see it, just do the rotation across this bond, okay? Keep the top part the way it is and rotate the bottom carbon. You'll see that this OH to the left will come here, the hydrogen goes to the right. So now you see you definitely can cut this molecule into equal half. So if you can cut this into equal half, then you can cut the other one to its right. You can cut this one right here into equal half, because after rotation of what's on pair 2, the second pair, after rotation of the bottom half, rotate this OH goes on to the left. You'll see that you have these two guys on the same side, and therefore you can cut it. The top part is reflected at the bottom. And that's what we define as meso compounds. They pretend to be enantiomers, because if I put a mirror here, they are reflected. They pretend to be enantiomers, but they are not, because they have internal plane of symmetries. Enantiomers must not have internal plane of symmetry. So pair 2 is meso. Pair 3 is meso 2. That's what I just drew here. You can get pair 3 by doing a rotation in pair 2 out of those two structures. And then pair 4 is not. If you look at pair 4, there's a problem, because the metals, let me squeeze it. Yeah, this metal up here is away. So here you can carry it into equal half, okay, but this guy you cannot, because this is down and this is up. In fact, if I'm to draw it in what we call Haworth projection, you'll see that the CH3 here is down and this CH3 is up. Okay, so this is up, this is down. There's no way you can cut this molecule into equal half. So the only answer you have here is pair 2 and pair 3 that are meso compounds. Okay, moving on. Question 10. What is the name of the molecule below? So the first thing you should notice is that you have an OH, so definitely the parent name is a phenol. So after you notice that this is the reference, then the whole thing is a phenol, because in this chapter I gave you the names of structures with substituents. That's a phenol. This would have been a toluene, and of course if you have an NH, the molecule will be called aniline. If you have OCH3, the molecule will be called anisole. So this is a phenol structure. So we're gonna give it its parent name, phenol, and then give the substituents the least number possible. So this is the correct numbering, not the other way around. So the name will happen to have an ethyl following alphabet rule. We write the ethyl before the methyl, E comes before M. Okay, that would be the UPAC name for that molecule. There's no hyphen here. It's just like that. Okay. So that's clear. Let's do 11. This one here is a toluene. You see this structure here? So the parent name will be a toluene, where you have a CH3 on the benzene ring is called toluene. But we do have substituents which are nitros. Give them the least location possible. So it's 3,4. So the name will be 3,4, and then there are two nitro groups. So it's di-nitro and then toluene. Because you have a CH3 on the benzene, the parent name will be toluene. Okay, moving on to number 12. The molecule below is an L sugar. The answer is true. For L, you just look down here. If OH is on the left, that's L. If the OH down here on the second last carbon, the first chiral carbon of the Fischer projection, if it were to the right, that would be called not A, it would have been called D. Okay, so the answer is true. This is an L sugar because this OH down here, which is sitting on the first chiral carbon of the Fischer projection of the sugar molecule, is on the left, so it's L. It's true. How many carbon chiral centers are in the Fischer projection below? So number 13. Usually, to read the Fischer projection, you read from the top, and anywhere they're crossing, there's a carbon. All right, how many chiral centers? You're looking for 4 different groups. This is not a chiral center because you have 2 groups, which are the 2 hydrogens on the same carbon. This is because you have an OH, you have a H, you have a carbon to an OH. This carbon on top is on hydrogens, so this has 4 different groups. I mark with an asterisk. This is also having 4 different groups. You have a H and an OH, those are different. And then you have this part right here, which is definitely different from the rest of the molecule. So that is another chiral center. And obviously down here, this carbon must be, because you have H and OH, those are 2 groups which are different. You have CH2OH, obviously going up, you don't have CH2OH, you have the rest of the big structure. So there are 3 chiral centers on that Fischer projection. So moving on, question 14. Okay, which of the following is not chiral? The answer is gonna be A and B because they have internal plane of symmetry. You see how A is drawn like this? I can easily draw it. This is the same as me drawing a ring, and then because the metals are equatorial up, I will do this. There, skip 1 carbon, skip this carbon, which is this, and do that. See, you have internal plane of symmetry. So this molecule is a chiral. Even though this carbon has 4 different groups, that has 4 different groups, the molecule has internal plane of symmetry, it has to be a chiral. Same story with B. You have internal plane of symmetry. I can easily carry it. So again, this is a chiral. So it's not chiral. But if you look at C, there's no way you can have internal plane of symmetry on C. There's no internal plane of symmetry on D because you have oxygen on the left, carbon on the right. So the answer is A and B. C and D are chiral. Okay. Next, which of the following is aromatic? Oh, we did this before. A is not aromatic again because it's not planar. You have this carbon right here, that's sp3. Okay, A is not aromatic. What about B? B is not, because it's gonna fail the 4n plus 2 equals number of pi electrons. It will fail. N will solve for a fraction. 4n plus 2 equals 2. We have 8 pi electrons. So you'll see that 4n equals to 6. If you take 2 on the other side, n will solve for 3 all over 2. So it fails the last rule, so this is not aromatic. C is not aromatic again because this carbon here has 2 hydrogens. So it's not planar. At that point is tetrahedral, and there's no conjugation. You cannot draw resonances. And then D is aromatic. I won't spend much time on this because I already explained to you what you need to be looking for. This is aromatic because it has 6 pi electrons. You don't count this lone pair because the nitrogen is already bonded to a double bond. I told you that. It's conjugated, it's cyclic, it's a planar. All the nitrogen is sp2, the carbons are sp2. It passes everything. So the answer is D. D is aromatic. Which of the following is aromatic? Okay, A is aromatic, B is not because this carbon right here is sp3 hybridized. You have 2 hydrogens right there. There's no conjugation. You cannot draw resonances towards this carbon. I've talked about C. C is similar to this A. The structures are the same. They are not aromatic because again you have 2 hydrogens there, making it not planar. And then if you are to consider the last piece, this guy has 4 pi electrons, so 4n plus 2 equals to 4. N will be equal to 1/2. That's a fraction. So the molecule fails the last rule, so it's not aromatic. So the answer here is this first structure. Okay. Oh, maybe I should explain why that one is aromatic for question 16. Let me draw it. I don't want to assume you saw it's aromatic. You see, you have a lone pair here. This lone pair can do resonances, so it's part of the pi electrons. We have 2 double bonds, so 2 electrons from the lone pair, 4 from the pi bonds. You have 6 pi electrons. Okay. And again, all these centers are sp2 hybridized. The nitrogens are sp2. The nitrogens are sp2. The carbons are sp2. This guy is sp2. Reason being, actually, this one should have had a negative charge. I'm assuming you would have known that if you drew the Lewis structure. So you have a lone pair and 2 bonds. That's sp2. 3 electron domains, 2 bonds and lone pair. And then the other lone pairs used in resonance. If you solve for n, you'll find that n is gonna be equal to 1. So it's aromatic. Okay, moving on to question 17. What's the major product? This is just bromination. You have your benzene ring, you're adding Br2, FeBr3. So the electrophile here has to be Br+, I told you that. So you just need a benzene ring with a Br somewhere, anywhere on those carbons of the ring. So the answer here is B, cannot be anything else. And then here, you still have electrophilic aromatic substitution. This is a toluene. Remember, alkyl groups are electron donating groups. They donate through bonds, so they are autopara directors because they are EDGs. So here I have Cl2 with the Lewis acid. So the electrophile, I told you Cl+. So you're gonna have either the Cl on the carbon next door. Okay, let's clean this up. You have the Cl on the carbon next door, or you'll have it on the para position. Okay, so this is ortho product, this is para product. Let's see what choices do we have. C is ortho, A and B are useless. So the answer is C, at least that's one of these. C is ortho. Choose structure C. So here, question 19, that's a Fredro Craft, but it's gonna be acylation. Both acylation and alkylation Fredro-Craft reactions, they fail whenever you have electron drawing groups presently on the benzene. So in this case, the answer is none of the structures will be made because this reaction will fail, because aldehydes, like ketones, each time you have a carbonyl structure, whether it's an aldehyde, a ketone, an ester, an amide, the carbonyl structure withdraws electrons from the ring. See, the dipole moments are showing you withdrawing electrons. So electron withdrawal deactivates the ring, and specifically Fredro-Craft reaction will fail. So the answer is none of the structures. Let's do the next reaction. Question 20. These are Fredro-Craft alkylation. Against alkyl groups activate the ring. So this is possible compared to question 19. Remember, again, I know it's Fredro-Craft, most likely because of the AlCl3. The electrophile here will be the carbocation when the Cl falls off. So that's what's going to be added on the ring. Because this is EDG, it's going to put the electrophile orthopara. So, two possible products. Two possible products. You're either going to put it there or you're going to put it here. This is going to be the para product, and this is the ortho product. So you look at structure D, that's the para product. Okay, and also structure C is the ortho product. So both those two, C and D, are possible. So structure C and D are correct. We still move on with aromaticity. I'm just gonna give you an overview. Which of the following is aromatic? This is not, because you have sp3 center here, the molecule is not planar, the molecule is not conjugated, you cannot draw resonances this or this way. This is not, because you're gonna fail the 4n+2 rule. Which question is this? 21. It's gonna fail the 4n+2 rule, even though it looks conjugated, because you can draw resonances this way, it's planar, everything is sp2, it's cyclic, it passes those three, but it fails 4n+2 rule. 4n+2 equals number of pi electrons. Obviously you have 4 pi electrons. If you solve for n is gonna end up being a half, so it fails this rule. So B is not aromatic. But you look at the next one, that's a furan ring. One of the lone pairs can be used in resonance, the other one stays to be counted as an electron domain. So you have 1, 2, 3 electron domains. The oxygen is sp2. Obviously this is sp2, 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 sp2. So the molecule is expected to be flat or planar. It's conjugated because I can do resonances. If you push this lone pair here, this is gonna be pushed here, this is gonna be pushed there. If you test for 4n+2, you have 6 pi electrons. Remember, we use this lone pair for resonance, and then we have these 2 pi bonds that move. They're affected by pushing this lone pair. So the answer is 6 pi electrons, 2 electrons from the lone pair, 4 from the pi bonds, and solves for 1. So this guy is aromatic. The next one is not, of course, those are CH2, tetrahedro. So the answer is just C. How many pi electrons are here? I just explained you're gonna need to have 6 pi electrons. It's the same ring. One of the lone pair in the oxygen will take part in resonance. So which means that lone pair is pi, because it affects the other pi electrons. When you push this there, this will be pushed here, and this will break and go here. So which means this lone pair is pi. So count the 2 electrons of the pi, count the 2, count the 4 from the pi bond, you end up with 6. So there's 2 in the lone pair, there's 2 here, there's 2 here. 2 plus 2 plus 2 equals to 6. I am not counting this because we've not used it in resonance. So the answer is 6 pi electrons. How many chiral carbon centers do we have in the structure? Now, to explain this, I probably will have to draw it. Okay, so the first one, there's a hydrogen here. So you have 4 different groups around that carbon. You also have 4 different groups around this carbon. This is an ethyl. Of course, going this way, you don't meet a nitrogen. Here you meet a nitrogen. So this side is different. H and ethyl are different. That's another one. So this center here is chiral. So so far those are 2. This one is another one. So that counts 3. And I don't seem to see any others. So there's 1 here, there's 1 here, and there's 1 there. These are on sp2 carbons, so they're not. So the answer is 3. What is the RS chirality of this molecule? So obviously there's a hydrogen here away. That is 1. And then hydrogen will be 4. Comparing CH3 and CH2, CH2 will win because this means this carbon is bound onto more carbons than this. So this will be 2 and this will be 3. Otherwise, just use your Kern Ingalls to track it. I'm not going to go through the whole steps. By now, I'm assuming you know how to quickly do it in this review. So that's an S. No, it's not. It's going clockwise, so it's not an S, it's an R because we're going clockwise. And we keep the R because the smallest group is away. So that was for 24. Or of 25. What is the chirality of the carbons marked with an asterisk? So this is assigning chirality on Fisher. Remember I said any horizontal line is going to be towards you. So let's assign the top one. I told you we always read it from the top. Let's assign the top one. Okay, so you see, assigning this carbon, this oxygen get priority 1, hydrogen priority 4. This carbon is bonded to, doubly bonded to an oxygen, so we pretend it's bonded to 2 oxygen. This carbon is bonded only to 1, so this will get priority 2, and this will get priority 3. So in which case we are going 1, 2, 3. You're going S, but the smallest group is towards because I told you the horizontal line in Fisher must be towards. So the true assignment here will be R. So we do the same thing for the other molecule, for the other center. I'm just gonna draw the same molecule again for purposes of explaining. Okay, so my concern now is this bottom one. You have OH and an H. You have CH3. So again, oxygen gets priority 1. Obviously, hydrogen before, and obviously this will be 3 because the rest, the carbon on top is bonded to more carbons. So this will be 2. So we are going 1, 2, 3. That's going S, but again the smallest group is towards us because it's on the horizontal line which is towards us. So the true assignment here, instead of S, this is going to be called R. So these two asterisks turns out to be RR. Okay, that's R, this is R. So the correct answer is RR. And last question in exam 2, question 26. What's the relationship? You see how these are on the same side, but these are on opposite side? You can quickly tell they're diastereomers. Otherwise, you can still again use this system and you'll see that one sentence kept, one is reversed. For example, I know just based on what we just did, we determined that these two centers are R and R, right? That's what we just did. So the other molecule will have the top one as R and the bottom one will be an S if you follow the same system. So if you are to compare, you have RR on the left structure and you have SS. You have RS, on the right structure. So basically, one stereo center is kept. This is kept, but this is now switched if you compare the two. So in this case, this is called diastereomers. So diastereomers is where one stereo center is kept and the other one is switched. Diastereomers. Okay, and that ends the review for exam